Welcome to the ancient and modern field of fluid mechanics. Fluid flows, gases or liquids, are all around us, from the very small to the very large, from the very slow to the very fast. Fluid mechanics is important in everything from sports and recreation to transportation to national defense. There are fluid flows inside our bodies as well as other fluid flows outside. We're going to start by introducing a wide variety of fluid flows, both experimental and computational, and discussing how these flows are classified. First, we classify flow regions as viscous or inviscid. Consider the viscous and inviscid regions in the flow over an airplane wing. This computational fluid dynamics, or CFD, animation shows colored contours of airspeed over a wing with an oscillating flap. Very close to the wing's surface is a thin layer known as the boundary layer. In it, viscous forces are important and cannot be ignored. However, outside the boundary layer, viscous forces are negligible compared to the inertia of the flow. We call this the outer, inviscid flow region. This distinction, due to Ludwig Prandtl, was one of the key developments in 20th century fluid mechanics. We also classify flows as internal or external. An internal flow is surrounded by walls, as in this computation of a train passing through a tunnel. Once the train is outside the tunnel, the airflow around the train is now an external flow. Likewise, flow over an airplane is external flow, while flow through a jet engine that powers an airplane is internal flow. Next, we classify flows as incompressible or compressible. Most liquid flows are incompressible. Thus, we keep the fluid density constant when we solve the equations of motion. Gas flows are also incompressible at speeds much less than the speed of sound, as in the airflow around a toy airplane or around a spinning football. However, high-speed gas flows are very compressible. Here's a high-speed movie of firing a rifle bullet and a simulation of a bullet emerging from the muzzle of a gun. Shock waves and other fluid phenomena happen here that cannot happen at low speeds. Another way to classify flows is laminar versus turbulent. Laminar flows, like the beginning of this plume from a candle flame, have smooth, ordered layers of flow with only molecular mixing between them. Turbulent flow occurs when the inertial forces dominate the viscous forces, which eventually happens at a higher location in the candle plume. Turbulence has unsteady, swirling vortices, or eddies, of various scales. These eddies cause strong mixing in turbulent flows, which are clearly much more complicated than laminar flows. Still another way to classify flows is natural versus forced. Natural flows do not involve fans, blowers, or pumps to move the fluid. Instead, it flows by itself as a result of some natural effect, such as buoyancy. Natural convection is sometimes sufficient to cool electronics, for example. Forced flows, on the other hand, are driven by some external means, such as the built-in fan in this laptop computer, or the water pump driving this pipe flow. Another classification of fluid flows is steady versus unsteady. By carefully adjusting the kitchen faucet, we can produce a stream of water that is not only laminar, but also steady, except for an occasional wiggle. The stream of water from this garden hose is turbulent, as one can tell from both its appearance and its sound. However, the water pressure that drives it, the nozzle diameter, and the speed of the stream are all constant on average if one ignores the turbulent fluctuations. We call this a stationary flow, or a flow that is steady in the mean. However, some flows, such as the gas flow inside an internal combustion engine, are inherently unsteady. The flow pattern is always changing with time. Even the boundary conditions are changing. As the piston cycles inside the cylinder, the volume available for gas motion, shown in this CFD simulation, varies periodically. In some applications, like this wing undergoing a slow pitching motion, we can approximate the flow as steady at any given instant, even though the flow field is really unsteady in principle. Such a flow is said to be quasi-steady. Our final classification is 1-, 2-, and 3-dimensional flows. Reality has 3 space dimensions. However, it's very useful in fluid mechanics to concentrate on fewer than these 3 dimensions for simplicity. For example, the flow through a pipe has 3 space dimensions x, y, and z, but often we're mainly interested in what changes along the pipe. Many pipes are so long compared to their diameter that we can neglect the change of parameters across the flow and consider only what changes with length of the pipe in the x direction. This is a one-dimensional flow approximation. Here is supersonic airflow through a converging-diverging Laval nozzle. One-dimensional inviscid theory in the x direction is sufficient to describe this flow, except for the viscous boundary layer at the walls. Here, these are quite thin and can be ignored. However, the flow over this wedge requires a two-dimensional theory in x and y. When the normal shock wave moves back up the nozzle, its interaction with the boundary layers becomes too complicated for any simple theoretical model. In the aerodynamics of birds and airplanes, we can often examine the flow in x and y over the cross-section of a wing and ignore any changes in the direction of the wing span z. Here is such an example in a wind tunnel where smoke is used to visualize the flow. The length of the airfoil in the flow direction is called its chord length. The airflow over a glider wing is approximately two-dimensional as well, since the wing's span is much larger than its chord. Such a wing is said to have a large aspect ratio. In this case, the wingtip and root are so far from a section at mid-span that they may as well be infinitely far away. A similar argument can be made for the wings of this waved albatross, more than 3 meters in span. The flow in a soap film is also very two-dimensional. The film's lateral dimensions are several centimeters, but the thickness is only a few micrometers, seen in color due to white light interference phenomena. On a global scale, the Earth's weather can be considered two-dimensional as well. In this NASA footage of Hurricane Isabel, the view spans thousands of kilometers, but the atmosphere itself is only about 100 kilometers thick. Thus, such large weather phenomena cannot go over the top of one another. They must go around. Often the gross features of a 3D flow can be observed by modeling the problem in only 2 dimensions. Here a buoyant, top-heavy block falls into a pool of water. A 2D CFD simulation reveals many features of this flow. The full 3D unsteady simulation shows some additional phenomena, but it takes at least 100 times longer to compute. In order to produce a fully three-dimensional flow, we fed theatrical fog into the bottom of this can. It makes a messy, turbulent 3D plume. A modern way to study such a complicated flow is to illuminate it by a thin sheet of laser light, thus slicing the 3D flow into two-dimensional sections. Many flows of practical interest are very three-dimensional. That's the case for the envelope of shock waves that surrounds this model of the Space Shuttle orbiter, here being tested at Mach 3 in a supersonic wind tunnel and imaged using a color Schlieren technique. Despite the complicated nature of this flow, we can still use approximate methods of fewer dimensions locally, such as a 2D flow approximation at the wing leading edge, to help understand the basic fluid dynamic building blocks that combine to make up real, practical flow fields.